Hi everyone. I hope you're doing well, and I miss teaching. I miss you all. I miss blowing stuff up and doing reactions, so I'm back again. I wanted to do some demonstrations for you and show you a little bit about decomposition and single replacement reactions. So my first one is going to be decomposition. So as you'll see, I've got a compound that is splitting up, and it could make two compounds, it could make an element in a compound, it could make two elements, but the main thing is you have one thing that's splitting up into simpler compounds or elements, substances. All right, so what we're going to do is this. Now, let's see, a little bit of practice. I want you to name it. Now, you've got to decide, in order to name it, you've got to decide, is this a covalent compound or is it an ionic compound? Well, you look at the periodic table. Okay, oxygen's obviously a nonmetal. Hydrogen's one of those strange ones because even though it's over there with the alkali metals, it's kind of by itself in its own little world. Well, hydrogen and oxygen, then what you have to do is electronegativity. So the electronegativity you find on the back of your ion sheet. So if you look at those two, I gave you an assignment a few weeks ago, and this, what you do is take the electronegativity values and subtract them. If you subtract them, it comes out to be 0.35, which is below 0.4, which means it's a covalent nonpolar compound. So that means that I have to name it with Greek prefixes. So the prefix for 2 is di, so I'm going to say dihydrogen, and then dioxide. I only want to put IDE on the very last element that I write. If I write 5 elements, the only one that gets I'd is the last one written. Okay, this one over here, let's name it dihydrogen oxide. I don't want to put mono because that would just not be, it's kind of like saying ain't to an English teacher. So since I already have the di on here, I don't need to put mono. So just dihydrogen oxide. Okay, gave you a little fun thing to do a few weeks ago. It was called DHMO, dihydrogen monoxide. And it was a little play on the fact that a lot of people see chemical names and they don't relate to what it really is. So I could name this dihydrogen monoxide. It would be incorrect, but it would fool people. So next time you want a glass of water, tell your parents you'd like a glass of dihydrogen oxide. All right, so let's balance this. I have 2 hydrogens, 2 hydrogens. I have 2 oxygens. I have 2 oxygens here, but I also have one there, so I have 3. Okay, now since I have an even number here, I need to make these even. I don't want to put a 2 here because I still have an odd number of oxygens. So let's try putting a 2 here. Balancing is just trial and error. You just go back and forth, back and forth. Now I have 2 oxygens plus 2 oxygens. So over here I'd need 4 oxygens. So if I put a 2 here, 2 times 2 makes 4. 2 here and 2 here makes 4. Okay, did the hydrogens work out? Yes, 4 and 4, so I'm good. Now this reaction, you probably have seen it if you were at my Halloween show. And what I have here, I was doing the monster toothpaste, Frankenstein's toothpaste. Well, what I have in the bottom of this graduated cylinder, I have some potassium iodide, which is just a kind of a white crystal. And I've put a little bit of water in there, and then I've just put some Dawn soap detergent. Because when I have the reaction, what I want it to do is make bubbles, and so I can see the bubbles come out. Now, the potassium iodide I use, that is my catalyst. And when I write the potassium iodide, I don't make it part of the reaction. I want to show that it's a catalyst because it's going to remain at the end of the reaction. I can actually get it back. So after it's done, if I want to go through the purification process, recrystallization, I can get the potassium iodide back. Nothing happens to it. It just makes the reaction happen. Okay, then I'm going to take some hydrogen peroxide. Now this stuff I have to order, the school has to order it for me, because this stuff is a lot stronger, a lot more concentrated than what you get at the Kroger's. Kroger's is about 3%, what you want to put on cuts. Now when you put it on a cut, it sometimes may bubble up. What it's doing, it's reacting with a catalyst in your blood. So same thing that I'm doing here, and it's producing oxygen gas and water. The oxygen gas, that concentrated oxygen, will kill a lot of bacteria and viruses. All right, so what we're going to do is now add my 30% hydrogen peroxide. Now I didn't add food coloring like I did at the Halloween show, but it should react the same. Okay, so you see the bubbles forming, and I want to see what kind of bubbles they are. Maybe they're hydrogen. If they were hydrogen, then it's going to explode. If it's CO2, the match will just go out. If it's oxygen, it's going to make the fire burn brighter. So let's take a look. So I'm going to take my match, and I'm going to see what type of gas it is. Okay, notice that the flame is burning brighter. Ooh, let's do that again. And so that means that I have oxygen gas being formed. So this is called the splint test. I'm using a match, or you could use a wood splint, but it's a splint test for oxygen gas. All right, now let's do single replacement reactions. So if you'll see my single replacement, I have a compound plus an element. Now that element, if it's a metal, it was going to try to replace the metal in this compound. If this is a non-metal, it'll try to replace the non-metal. But this only happens if C, the single element, is stronger than the element that's bonded in the compound. If it does react, then it's going to take its place. So C is going to come over, kick A out. A is now all by itself, and now you have a compound plus an element. How do you recognize it? You have a compound plus an element, and you get a compound plus an element on this side. You could have something else, but this is the basic structure. All right, so let's predict. I've got copper metal, and copper is trying to kick calcium out and take chlorine away and bond with it. So let's see which of these two is stronger. So if you'll get your handy dandy ion sheet, and you can see right here you've got calcium, and then where do we have copper? Copper's all the way down here. So notice it says least reactive, more reactive. So that means that calcium is more reactive than chlorine. So if calcium is stronger, it's not going to let it take chlorine away. It's like this guy wants to take this guy's girlfriend away. Well, I mean, the girlfriend should have some say in it, but we're going to ignore her feelings for now. That copper is not strong enough to kick calcium out. So calcium says, I'm going to keep my girlfriend. All right, now I have here, this has been sitting around for quite a while, about 20 minutes. And if you'll notice, I've got the calcium chloride solution, I have the copper piece of metal, and I see no reaction at all. Nothing's happening. So we predicted no reaction, and that is what we got. And so you're going to put no reaction. You're not going to have any products because these two are going to stay the same. And over here you just write no reaction, or you could write NR. All right, let's take magnesium and silver nitrate. Now magnesium, I did that in the synthesis where we made magnesium hydroxide. Here I have some magnesium. I usually keep it in the flammables cabinet, but if you see, I've got there it is. Remember the safety diamond that we had at the beginning of the year, and this will tell me how reactive it is and some other information. What does that W with a line drawn through it mean? It means do not come in contact with water or it might react. Okay, so if you'll notice over here, reactivity of 2, so it's fairly reactive. 4 would be the most. If I want some more information about magnesium, then I'll look at the material safety data sheet called MSDS, sometimes called SDS, safety data sheet. And it will tell me a whole lot of things about it. This is 1 page, or basically 2 pages. They can be up to 9 depending on how much information you want. But it'll say, is there a fire hazard? How do you transport it? How do you clean it up? How do you dispose of it? So lots of good information in the material safety data sheet. Okay, so here I have some silver nitrate. I've dissolved it up into water, and I want to make sure that it's dissolved. Now, when you stir it up, you can put a cork on it and shake it. Sometimes the cork might leak. Some people take their finger and shake it up, and that's a no-no. So the easiest way, the safest way to stir up what's in here would be to take a stirring rod. But if you don't have one available, hold it between your fingers and gently flip, and it will swirl the solution inside. So just gently, gently. I want to make sure this is all stirred up. Now I'm going to take some magnesium and put it in the solution. Now magnesium's such a soft metal. I can just tear a piece off with my hands. So there's the magnesium. Again, it's got a little coating of magnesium rust on the outside. That's why it's not really shiny. So the magnesium oxide is the rust. All right, so I'm going to drop it in here and see if you can see what is happening. Can you see a reaction? Is it immediate or not? Okay, I can see already the strip of magnesium's turning dark, and it looks like something's growing on it. This one I've had sitting out for about 20 minutes. And as you can see, the magnesium strip, it was the same length as what I had over here. But right now you can see all this kind of blackish stuff. That's actually silver. And silver is just not shiny like it's not polished up. But this is actually silver. Now, you might say, oh, I can make this. I could take this and clean it up and make it into silver jewelry. You can, but to buy this silver nitrate costs more than just to go buy the silver. Okay, last one we're going to do, oh, you know something? We did not balance it. I didn't even predict it. Okay, we did see a reaction. Well, let's see, does that make sense? Okay, let's take a look at magnesium. And I see magnesium right here, which is fairly reactive. I see silver. Silver's all the way down here. So magnesium is stronger than silver, so it should kick it out, and it did. We saw it react. So yes, we had a reaction. So how do I know what's forming? This is a metal, and this is a metal. This part is my negative. Remember, this is positive, this is 0 because it's just still an element. So my magnesium kicked silver out, so I have silver by itself, plus I have the Mg now with the nitrate. Now, I cannot leave it like that. First of all, I have to check and see, is silver diatomic? No. Is magnesium diatomic? Well, it's not, but it doesn't matter because it's in a compound. Diatomics don't apply in compounds. But I do know that the charge is 2+. If you look on your ion sheet, that's -1. So I have to put my 2 down here, my 1 down here, crisscross. Now I've got to balance it. I've got 2 nitrates, so I'll need 2 nitrates here. 2 nitrates, 2 nitrates. But I messed up the silvers. I got to fix it. So 2 silvers, 1 magnesium, 1 magnesium. I've got it balanced. All right, let's try the next one. Hydrogen is trying to get not kicked out by zinc. So I want to know, is zinc strong enough to kick out hydrogen? Okay, so let's see. I've got zinc right here, and then I've got hydrogen right there. So is zinc strong enough to kick hydrogen out? Yes, it is. So zinc should react. So zinc and hydrogen, those are my 2 metals. Zinc is going to kick hydrogen out. Hydrogen's going to be by itself. Hydrogen is diatomic. You look on this diatomic list of elements, and I do see hydrogen. Again, it's not diatomic over here, it's in a compound. All right, so zinc is now going to join up with the chlorine. Okay, I've got to check my charges. 2 plus, 1 minus, crisscross. That means I have 2 chlorines on this side, so I have to have 2 over here. Then I have 2 hydrogens. I have 2 hydrogens, so good. Okay, I'm going to put some hydrochloric acid. Now this says 6 molar. And 6 molar, well, what does that mean? It is the molarity. And the molarity of pure hydrochloric acid that you get from the chemical company, it is 12 molar. That is the most concentrated you can get. So 6 molar would be how much? Figure it out. 50% acid. So it's fairly concentrated. Okay, now I am going to put some of that Okay, let's take some zinc. I've got granulated zinc. Which is a beautiful silvery type metal. Let's get a little bit more. And let's get this a little closer. Okay, you can already see it starting to bubble. All right, now again, let's test that gas. I'm going to test and see what it is. I say that it's hydrogen from my reaction. Let's see if it is. If it's hydrogen, it's going to explode. How's that? Kind of between a pop and a squeak. Okay, it's not doing it. I need to build up a little bit more gas in order for it to pop again. Just not enough concentration. All right, let's wait for a minute. Let's try it again. And there you have it. Hydrogen gas is being produced. Okay, final reaction. Okay, this one is between copper 2 chloride and aluminum. And I'm going to do this a little bit different way. I'm not going to do it in the test tube. This is a lab that we do, or we would have done this year. And what you take is aluminum, and to make a little fun with it, I have you all make a boat. And so we're going to take our boat and we're going to mix it with, we're going to sprinkle some copper 2 chloride on it and see if it reacts. First of all, I want to see is, does aluminum react with the copper 2 chloride, just dry? Does the aluminum react with water? Because I have a swimming pool for my boat, and I'm going to see if aluminum reacts with water. And then I'm going to see if I add water to both the copper 2 chloride and the aluminum, then does it react? All right, so let's try. All right, let's fill the boat up with some water, the swimming pool. Put some water in here. Ugly duckling swan boat. Now, I can see I've got the aluminum with the water, nothing's happening. Okay. All right, now let's take the copper 2 chloride, mix it with a little bit of water. Copper 2 chloride. Most copper compounds are this beautiful kind of a bluish green. And it's like the Statue of Liberty. You know, she has changed from being copper to a copper compound. That's why she's greenish. All right, so let's take and see if it will react just with the water. And it's dissolving, but I'm not seeing any reaction. It's turning the water blue because it's dissolving, but no reaction. All right, now let's take the copper 2 chloride and we're going to put it onto the aluminum. No reaction. Okay, so here you have, I've got the copper 2 chloride in on top of the aluminum and I'm not seeing any reaction. But let's put some water in it. Oh, pretty cool. Now it's produced some gas. It's pretty hot. I can feel the heat coming off of it. So it's fairly hot. That means it's an exothermic reaction. The energy of the products are lower than the energy of the reactants. And I can see this kind of a reddish stuff coming out. Now this is not rust. This is actually copper. So this is copper metal. And you can see the bottom of the boat has been completely eaten through. That means that the aluminum has reacted, the copper has come out of the solution. So copper came out of the compound. And if I could take this copper and purify it, I could make pennies out of it. All right, let's take a look at the reaction. Should it react, take a look at your ion sheet. And you can see that copper is higher up than aluminum. Copper is more reactive. That means it should have reacted, so I should get a reaction. So the Al and the Cu switch places. So Al comes over with the chlorine, and copper gets kicked out by itself. And we saw that happen. We saw the reddish copper come out of solution. Okay, check your charges. Crisscross. This is charge of 0. It's not diatomic. 3 chlorines, 2, 2 and 3, think common multiple 6. So I'm going to put a 2. 2 times 3 makes 6 chlorines. And I put a 3 here. 3 times 2 makes 6 chlorines. 3 coppers, 2 aluminums, 2 aluminums. And there you have it. I hope you have a wonderful day. Thank you so much for watching, and I'll see you next time. Bye.